Hello students, the next application which we will try to understand is op-amp as subtractor, or it can be used as a differential amplifier. I'll explain what exactly it means. See, in all the previous examples, what we did is op-amp as op-amp as inverting amplifier, op-amp as non-inverting amplifier, op-amp as buffer, op-amp as sign changer, op-amp as adder. In all this application, what we did is either we connected op-amp in inverting mode or in non-inverting mode. This is the only application, op-amp as subtractor or differential amplifier. Here we will give two inputs to two variables connected to two different inputs of op-amp. Of course, we know we have two inputs of an op-amp, inverting and non-inverting. And if you remember and you can recollect the block diagram of op-amp, the first block of the operational amplifier is a differential amplifier which amplifies the difference between the two input signals. So that is what we are going to use as an application for op-amp as subtractor. So what I said, we will have two inputs given to two different terminals, inverting and non-inverting. So this is the only example where we will do that. Okay, so see the diagram, circuit diagram. You have inverting and the non-inverting terminal. When you use op-amp in inverting mode, you connect the non-inverting terminal to ground and input is given to the inverting terminal. When the op-amp is connected in non-inverting mode, what you do is input is given to the non-inverting terminal and inverting terminal is grounded, right? But here in this case we will provide two inputs. Okay, two inputs. I will call these two inputs as V1 and V2 given to two terminals, inverting and non-inverting. Okay, of course we have two power supply, plus VCC and minus VCC, and here we will take the output with respect to ground. Now we have to use it as a differential, we have to use it as an amplifier. If you don't provide negative feedback, the gain will be infinite, and if the gain is infinite, the output will be either plus VCC or minus VCC. We have seen that in the previous videos. So if you don't provide negative feedback, the circuit will not work as amplifier. So if you have to use it as an amplifier, the gain should be finite, and for the gain to be finite, you have to give negative feedback. Of course, this resistance we called it as feedback. In this case, I will call it as R2. Okay, let this potential be VA. One more resistance from this point, from where the non-inverting terminal is there, we have to connect it to ground. The resistance value will be same, R2. Okay, so this is the diagram for op-amp as subtractor, or it can be used as a differential amplifier. Okay, so the first thing which we will understand is, see, these 2 points, I'll call this point as VA and VB. Now what happens, the differential amplifier, when you give two different inputs to the two different terminals, the difference of the two is called as error voltage, right? Error voltage, and that at that point the gain is infinite, therefore the difference between the two will be 0. Okay, so we say V error equals to V equals to VB minus VA, right? And that will be output upon AOL, and output upon AOL is infinite, so V0 upon infinite, that means it will be 0. Or we say V is equal to VB is equal to VA, right? We can conclude this. So what we have considered is the potential at this point is V. Okay, both at equipotential, and therefore we consider that voltage to be V. Okay, now as the input impedance of op-amp is very high. What we can conclude? See, as soon as V1 is applied, current I1 will flow. I1 will flow up to this point, right? And as the input impedance of op amp is very high, no current will flow through op amp, all the current will flow through R2. Let that current be I2. So what we can conclude is I1 is equal to I2. Let this be equation number 1. Similarly, when V2 is applied, current say I3 flows up to VB, and as the input impedance of op amp is very high, no current will flow through op amp. When I say input impedance of op amp, we have already studied in the ideal characteristics. Input impedance is infinite, that is resistance offered by the op amp at the input side. So I3 current will flow up to VB, and as the input impedance of op amp is very high, all the current will flow through this R2 to ground, so that current will be I4. So from the figure we can say I3 is equal to I4. Let this be equation number 2. Okay, now what is I1? I1 is the current flowing through R1, and R1 is connected between which two points? V1 and V. So it will be V1 minus V upon R1. Similarly, what will be I2? I2 is the current flowing through R2. R2 is connected between which two points? VA and V0. So V potential at VA, we have considered it at V. So it will be V minus V0 upon R2. V minus V0 upon R2. Okay, let this be equation number 3. Substituting the value of 3 in 1. What you get is V1 upon R1 minus V upon R1 equals to V upon R2 minus V0 upon R2, or I can say V1 upon R1 equals to V upon R1 plus V upon R2 minus V0 upon R2. Let this equation be star. Okay, now similarly what is I3? I3 is the current flowing through R1, and R1, this R1 is connected between which two points? V2 and V. So it will be V2 minus V upon R1. And what is I4? I4 is the current flowing through this R2, and this R2 is connected between which two points? VB and ground. So potential at VB is V. So V minus ground potential is 0. So V minus 0 upon R2. Let this be equation number 4. Substituting the value of 4 in 2. This equation, what you get? V2 upon R1 minus V upon R1 equals to V upon R2, or the same thing can be written as V2 upon R1 equals to V upon R1 plus V upon R2. Let this be equation number 5. Okay, so V upon R1 plus V upon R2 can be replaced by V2 upon R1 in this equation. So substitute the value of 5 in star. So what you get is V1 upon R1 equals to, what is V upon R1 plus V upon R2? According to equation 5, it is V2 upon R1 minus V0 upon R2. Okay, so I'll take this V0 upon R2 on the left hand side and V1 upon R1 on the right hand side. So what I'm going to get, the equation is V0 upon R2 equals to V2 upon R1 minus V1 upon R1. Okay, or the same equation can be written as V0 is equal to R2 upon R1 V2 minus V1. Okay, V2 minus V1. Now in this equation, if I make R1 and R2 same, what I'm going to get? If I make R1 and R2 same, this equation becomes V0 is equal to V2 minus V1. That means output is difference between the two input voltage. That means it works as subtractor. And if I need a gain, if I want to use the circuit as differential amplifier, then what I should do? I should select proper values of R2 and R1. Say I want a gain of 10. Okay, 10. So what should I do? Say I keep this R2 value as 20 ohms and R1 value as 2 ohms. So 20 divided by 2, 10. So 10 multiplied by the difference between the two. So of course it will be a differential, right? Differential output also it works as amplifier. So you can easily, if resistance, all the resistance value are same, it works as subtractor. If R2 is more than R1, it works as differential amplifier. Okay, so this is the output voltage equation for op amp as subtractor. Okay, op amp as differential amplifier, of course, and if I make R2 equals to R1, the same circuit can be used as a subtractor. Next is numerical based on op amp as subtractor. Say this is the circuit diagram. Of course, the question will be calculate output voltage of the following circuit. Okay, you need to identify in which mode the circuit has been connected. Okay, of course, I have clearly mentioned here it is an op amp as subtractor, but it is a very easy way to identify that two inputs are provided to two different terminals. Okay, two inputs are provided to two different terminals. In all other applications, either the op amp is working as inverting mode or in non-inverting mode, but in op amp as subtractor, two different inputs will be provided to two different terminals. So that is how you can easily identify. Okay, now the input resistance R1 is 5 ohms, output resistance or R2 is 10 ohms, plus VCC and minus VCC is plus 10 volt and minus 10 volt, and the inputs are 2.54 and 3.12. Very important thing which has to be remembered, and in the previous section we did obtain the output voltage for op amp as subtractor, and what you have seen is it is always V2 minus V1, and V2 was the potential applied at non-inverting and V1 was the potential applied at inverting. So whenever you use op amp in subtraction mode, right, op amp as subtractor, the difference will be always non-inverting minus the inverting. V2 minus V1. V2 is the potential applied at non-inverting, V1 is the potential applied at inverting. This has to be remembered always. Okay, now what is the output voltage equation? V2 is R2 upon R1, V2 minus V1, and in this case what is R2? R2 is 10 ohms, R1 is 5 ohms. These two resistance will always be same, these two resistance will always be same. Okay, so whatever be the value, you have to just mention there, and you have to substitute this value in this equation so that you get the answer. So V2 is 10 upon 5. What is V2? V2 is 3.12 minus 2.54. Okay, so V0 is 2 multiplied by this value will be 1.42. So V0 will be 2.84 volts. Okay, here in this case we are using this circuit as differential amplifier. Of course, it is finding out the difference between the two input, but there will be an amplification factor because R2 and R1 has a different value. Okay, so if this value would have been same, what you can see is V0 is equal to 1.42, which is the difference between the two input voltage, then it would have worked as subtractor. Okay, the next application we will try to understand is op amp as integrator. Now just look at the diagram which I have drawn on the board. Now this diagram has non-inverting terminal grounded, input is applied to the inverting terminal, and there is a resistance which connects the some part of the output back to the input through a feedback resistance RF. So if you closely look at the circuit, this is nothing but op amp as, yes, op amp as inverting amplifier. Okay, I will make some modification so that op amp can be used as a integrator. Okay, so the circuit remains the same, op amp as inverting amplifier. The only modification which has to be done in op amp as inverting amplifier to make it op amp as integrator, that we replace the feedback resistance by a capacitor. That's all. Okay, by a capacitor. Now let us try to understand what exactly we mean by op-amp as integrator. See, what is integration? You all know what is integration. Integration is when we keep on adding a data, right? We keep on adding a data over a limited bandwidth. In this case, in op-amp, I can say that over a limit, if I keep on adding small data, that type of circuit can be called as integrator. Now please recall the last ideal characteristics of op-amp. We said slew rate must be 0. What does that mean? What is slew rate? Slew rate is the rate of output to reach to its final value as soon as input is changed. Input change होने के बाद में output को अपने final value तक पहुंचने के लिए जो time लगेगा उसको हमने बोला slew rate, and we say ideal characteristic it should be 0. That means as soon as input is applied, the output should become 0. The output should go into the output should reach to its final value. But sometimes we need that the output should change with respect to time. It should not reach to final value immediately. It should reach with respect to time. So we need to have a time constant. Okay, time components we have to include in the circuit. So that's why we have replaced the feedback resistance by a capacitor. Now R and C forms a time component. So the output now will not change to final value immediately. It will change with respect to time. It will keep on adding up small values, and it will reach to its final value over a period of time. So that is why this circuit is called as op-amp as integrator. Okay, now what you can see is, let the current, when input Vi is applied through Ri, let the current which will be flowing is I. Okay, now what you can see is, in case of op-amp as integrator, the capacitor is connected between 2 points. The summing point, as the circuit is working in inverting mode, the summing point will be at virtual ground. That means the potential at this point will be 0. So capacitor is connected between which 2 points? V0 and virtual ground, and the output is taken between this point, the same point, and ground. That means the output voltage, the entire output voltage drops across the capacitor, or I can say the output voltage is equal to the voltage across capacitor. So from the figure we can say, I will explain once again. I hope you have understood. See, what I said is capacitor is connected between this point and the ground, because summing point is at virtual ground, as we have connected the circuit in inverting mode, and from the same point and ground we are taking the output voltage. So it is as if we are taking the output voltage across capacitor. So output voltage will be equal to voltage across capacitor, and voltage across capacitor is given by Q by C, charge stored in the capacitor divided by capacity of the capacitor. And as the input is connected to the inverting mode, so I will say it will be V0 is equal to minus Q by C. Okay, this minus sign indicates there is a phase shift of 180 degree between input and output. Okay, now by definition of current, what is current? Current is rate of flow of charge. Okay, so what is I is equal to d dt of Q. Okay, so let this be equation number 1, let this be equation number 2. Okay, so sorry, not this equation. I is equal to d dt of Q. I can write the same equation as I dt is equal to dq. Okay, integrating both sides, so it will be integration of I dt is equal to integration of dq. Integration of dq will be q, so q is equal to integration of I dt. Let this be equation number 2. Substituting the value of 2 in 1, So what you get is V0 is equal to minus, what is Q? Q is integration of I dt, and as C is constant it will be taken out, so it will be 1 upon C integration of I dt. Let this be equation number 3. And now what is I? I is the current flowing through Ri, and Ri is connected between which two point? Vi and summing point, which is at virtual ground. So I will be potential difference divided by R, so it will be Vi minus 0 upon Ri, or I can say Vi upon Ri. Let this be equation number 4. Okay, substituting the value of 4 in 5, what you can get, 4 in 3, what you get is V0 is equal to 1 upon C integration of Vi upon Ri dt. As Ri is constant, it will be taken out. Vi is equal to minus 1 upon Ri into C integration of Vi dt. So this is the output voltage equation for op-amp as integrator. Now what you can see is we can make sure that by selecting proper values of RC, say if I select R as 1 meg ohm, that is 1 into 10 to the power 6, and capacitor as 1 microfarad, so 1 into 10 to the power minus 6, these two will cancel each other. So by selecting proper values of R and C, I can make sure that the value becomes 1, and if that is 1, V0 is minus integration of Vi dt. That means output is time integral of input voltage, and this negative sign indicates that there is a phase shift of 180 degree between input and output. Okay, so that is how we can use op-amp as integrator. I hope you have understood. Next we will try to understand a numerical based on op-amp as integrator. As I said, the output will not reach to its final value immediately, it will reach with respect to time. So of course what you can see is, you can see the diagram. If there is a capacitor connected at the output stage, you can easily identify that the output the circuit is connected as a integrator. Okay, so here it has been mentioned that the capacitor value is 10 microfarad, input resistance is 100 kilo ohms, and input voltage is 2 volt. The question will be like this: calculate the output voltage at time interval 0.5 second, 1 second and 2 second. Okay, so at different time interval you have to calculate the output voltage. So what is expected? The output will keep on increasing with respect to time to reach to its final value. Okay, so what is the formula? This is op-amp as integrator. So op-amp as integrator has a formula: V0 is equal to minus 1 upon RC integration of Vi dt. What is R? R is 100 kilo ohms, that means it will be 100 into 10 to the power 3 ohms. C is 10 microfarad, 10 into 10 to the power minus 6 farad, and Vi is equal to 2 volt. Now in this equation, V0 is equal to minus 1 upon RC. Vi is already fixed 2 volt, which is a constant quantity, so it will come out. So it will be Vi upon RC integration of dt. And what is integration of dt? Integration of dt will be t. So it will be this formula: V0 is equal to Vi upon RC into t. Now substitute the value, of course, with a minus sign. So minus 2 upon 100 into 10 to the power 3 multiplied by 10 into 10 to the power minus 6 multiplied by what is t. Now t has 3 different values, so say 0.5. So V0 is equal to minus what? How much this value will be? 100 into 10 to the power 5 multiplied by 10 to the power, this is minus 5, this will cancel each other, 0.5. So V0 is equal to minus 1 volt. 2 multiplied by 0.5 will be 1 volt. So this is for the first case when t is equal to 0.5 second. Second case, t is equal to t is equal to 1 second, so V0 will be 2 volt, minus 2 volt, and third, when t is equal to 2 seconds, V0 will be minus 4 volt. You can substitute the value and you will get these answers. Okay, so what you can see is with respect to time, the output voltage is gradually increased. So sometimes in some application we need that the output to increase with respect to time. And if you remember, we use the same circuit op amp as integrator in the block diagram of function generator. If you remember, integrator, the output of the integrator will give you a triangular waveform. That means the output gradually increases to a particular value. At this point, the circuit will be switched, and then the output will be the output voltage will decrease, and that will keep on happening. Switching happens, and the output of the integrator will provide you a triangular waveform. If you want, you can just go to that particular video and you can see function generator. The output, the first input which we provide from the upper and lower constant current source, we provide it to the integrator, and the output of the integrator provides you the triangular waveform. So we have already used this circuit in the circuit of function generator. So this is all about op amp as integrator. I hope you have understood. Next application is op amp as differentiator. Of course, the output voltage will be time differential of the input voltage. That is what we have to prove, that this circuit can be used as op amp as differentiator. Now just look at the circuit which I have drawn on the board. What you can see is, again, input is applied to the inverting terminal, non-inverting terminal grounded, and feedback resistance is provided. That means this is op amp as inverting amplifier. Now I'll make a small modification. As I say, it should be a time differential. Output should be a time differential of the input voltage. So I need to give a time factor. For that, what we do is we replace the input resistance by a capacitor. So input Vi will be applied between this point and ground. There is a capacitor which is, and as we are connecting it in the inverting mode, this is the summing point, which is a virtual ground. This is resistance R. Now when Vi is applied, current I1 will flow up to this point. As the input impedance of op amp is very high, all the current will flow through R. So we can say I1 is equal to I2. Okay, so first thing which I'll write is, as the input impedance of op amp is very high, what you can say is I1 is equal to I2. Let this be equation number 1. Now from the figure, what you can write, see, input voltage is applied between this point and ground, and capacitor is connected between the same point and summing point, which is also at ground. That means these two comes in parallel. That means Vi is equal to voltage across capacitor. So now from the figure we can write Vi is equal to voltage across capacitor, and voltage across capacitor is given by Q by C. So I can write this equation as Q is equal to Vi into C. Let this be equation number 1. Okay. Now, by the definition of current, what is definition of current? Here I'll take that I1 is equal to d dt of Q. Okay, and I1 is equal to, what is the value of Q? Q has been taken as d dt of Vi into C, where C is the capacitors, which is a fixed value. So I1 is equal to C d dt of Vi. Let this be equation number 2. Okay, now what is I2? I2 is the current flowing through the resistance R, and R is connected between which two points? Summing point and output voltage. So difference, potential difference divided by resistance, so it will be 0 minus V0 upon R, or I can say V0 or minus V0 upon R. Let this be equation number 3. Substituting the value of 2 and 3 in equation 1. What you get is C d dt of Vi is equal to minus V0 upon R. So V0 is equal to, what will be the formula? Minus RC d dt of Vi. And as I said, of course, this will be the output voltage equation for op amp as differentiator. And if I select proper values of R and C, I can make the value as 1. And if this value is 1, V0 is minus d dt of Vi. That means output voltage will be time differential of input voltage. And this minus sign indicates there is a phase shift of 180 degree between input and output as the circuit is connected in inverting mode. Okay, so this is how we can use op amp as differentiator. Output voltage will be time differential of input voltage. Okay, the next application is op amp as comparator. Of course, what you can see on the board, I have drawn 4 circuits. That means there are 4 ways in which the op amp can be used as a comparator. Now, just the most important point which you have to see in the circuit is that what I have done is, in the first 2 cases, either I have applied input to the inverting terminal or input to the non-inverting terminal. And in the next 2 cases, input has been applied to 2 different terminals, both inverting as well as non-inverting, you can see, right? But the most important part which has to be understood is that there is no feedback resistance. Okay, there is no feedback resistance. And what is the use of feedback resistance? See, what we have done is, feedback resistance we have applied to suppress the gain, so that gain becomes finite and we can use that circuit as an amplifier. Now here there is no feedback resistance, and if there is no feedback resistance, the gain will be infinite. So output is the difference between the 2 input voltage multiplied by gain. So I will explain it. Okay, V0, okay, V0 is equal to gain multiplied by difference between the 2 input voltage, right? So the difference will be, say, I will always write it as V2 minus V1, where V2 is the potential applied at non-inverting terminal and V1 is the potential applied at inverting terminal. Okay, so in the first case, and gain is, as no feedback is given, gain is infinite. So of course the output voltage either will be plus VCC or minus VCC, because we know in op amp output cannot be more than the power supply which we are going to give, right? So the power supply maximum saturation is plus VCC and minimum saturation or the negative saturation is minus VCC. So the output will be either plus VCC or minus VCC, because gain is infinite. Okay, so now gain is infinite. Okay, gain is infinite because feedback resistance is missing. Now if Vi is greater than 0, as I said, inverting 0 crossing detector, it can, we know that when the circuit is going to cross the 0 mark. Okay, if Vi is greater than 0, what is the difference? This is 0 and this Vi is greater than 0. If it is greater than 0, then what you can see is 0 minus anything higher value will be minus, okay, in subtraction. So this difference will be negative, and gain is infinite, so output will keep on increasing up to negative saturation. So if Vi is greater than V0, sorry, Vi is greater than 0, V0 will be minus VCC. And in the same circuit, if Vi is less than 0, if Vi is less than 0, that means the subtraction between these two will give you a positive answer. So positive gain is infinite, so output voltage will keep on increasing till the positive saturation. The output will be plus VCC. Okay, so if we can say the output is minus VCC, we can say the input voltage is still greater than 0 volt. and if the output changes from minus VCC to plus VCC, we can say the output has now gone from positive to negative. That means it has crossed the zero mark. So that is why it is called as zero crossing detector. Okay. Next, non-inverting zero crossing detector. That means here input voltage is applied to the non-inverting terminal and inverting terminal is grounded. Now again the output voltage is gain multiplied by difference between the two input voltage. In op amp, as subtractor we understood that the difference will always be non-inverting minus the inverting. Okay, so it will be V2 minus V1. That means voltage across non-inverting minus voltage across inverting, and gain is infinite. Now if here we say Vi is greater than 0. Okay, Vi is greater than 0. Now what happens? What is Vi? Vi is applied to the non-inverting terminal. That means V2 is greater than Vi. That means V2 is greater than V1. V1 is ground. So here the potential is 0, and V2 we have considered the V2, the potential applied at V2 is Vi, and Vi we have considered it is to be greater than 0. So if it is greater than 0, the difference will be positive and V0 will be plus VCC. Okay, similarly if Vi is less than 0, then what will be V0? If Vi is less than 0, that means this is 0, and Vi, which is a voltage applied at V2, if it is less than 0, the difference will be negative, and the output will keep on increasing till minus saturation. So if you have non-inverting zero crossing detector, what you can see is if the input voltage, if the output is positive plus VCC, we can say that the input voltage is still greater than 0, and if the output changes from plus VCC to minus VCC, we can say the input has crossed 0 mark. Okay, that means it is less than 0, it will be cross 0 mark. So that is how it will be it can be used as a non-inverting zero crossing detector. Okay, in the next two circuits, instead of connecting the other terminal to ground, we have given reference voltage. Okay, so reference voltage will be compared with the input voltage, and these two voltage will generate output correspondingly if it is inverting or non-inverting. So we say inverting non-zero reference comparator, and here non-inverting non-zero reference comparator. Same formula, V0 is equal to gain multiplied by V2 minus V1, where V2 is the potential applied to the non-inverting terminal, V1 is the potential applied to the inverting terminal. Okay, here also gain is infinite. Now if Vi is greater than V reference, in this case Vi is greater than V reference. Okay, so the potential applied at inverting is greater than potential applied at non-inverting. So the difference between these two, that means non-inverting minus the inverting, the difference will be negative. So V0 will be minus VCC, and if Vi is less than V reference, V0 will be plus VCC, right? Vi is less than V reference, that means voltage across V reference is greater than Vi, so difference between these two will be positive, so output voltage will be plus VCC. So that is how two input voltage can be compared. Last one, non-inverting non-zero reference comparator. V0 is gain multiplied by V2 minus V1. Gain is infinite if Vi is greater than V reference. V0 will be equal to, now Vi is greater than V reference, that means the difference between the Vi is applied now to the non-inverting terminal and V reference to the inverting terminal. So the difference between these two, if Vi is greater than V reference, the difference between these two will be positive, therefore V0 will be plus VCC, and if Vi is less than V reference, V0 will be minus VCC. So these are the four conditions. Just draw the diagram, write this condition, that's all. This question will be asked for 3 marks, and this is more than enough for you to write and get the marks. I hope you have understood.